Hi, so what I'm going to talk to you today is going to be about derangements. Now, if you're following along in the text, then you understand that what a derangement is a permutation from what we see here, an n set to itself such that no element gets sent back to itself, right? And so what we want to avoid in this case is any element being fixed, like 1 going to 1 or 2 going to 2 or anything like that. And this is sort of a difficult thing to count directly, but since we've proven the principle of inclusion exclusion, that can be a big help to us. So the first thing we want to note, of course, is that there are n factorial permutations, right? If I just didn't care about anything, there's n factorial ways to send n elements to themselves. So I want to take these n factorial, and what I want to do is get rid of anything that fixes anything, right? Any permutation that will send any element back to itself. Now, what this looks like then is we take our n factorial and now we have to count how big is the collection of permutations which sends anything back to itself. So the way we want to think about it is, well, it's the union of the stuff that sends 1 to itself, or sends 2 to itself, or sends 3 to itself, or sends 4 to itself, etc. And that suggests a PIE type of argument. So let's talk about how many ways can we send an element back to itself. Well, there's n choose 1 ways to pick an element, right? We send it back to itself, and then there's n minus 1 elements left, right? And we just rearrange them however we want. Now, clearly there's going to be a lot of overlap between all of these, because let's say I pick 2 and I fix 2 and I just rearrange everybody however they want to be arranged, then maybe 3 goes back to itself or 1 goes back to itself and so on. And so this is where the PIE comes in. We have to go through our alternating sum now. So we subtract from that, taking away 2 elements, picking 2 of the elements, fixing them, sending the remaining n minus 2 factorial back to itself, adding in, pick 3 elements, fix them, send the other n minus 3 elements however we want, etc. Blah 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 until we have pick n choose n and send none of the elements now back to themselves. And so if we do this, we will, and then the sign here depends on n, right? So it's minus 1 plus minus 1 to the n plus 1. And we can sort of rephrase this whole sum, again distributing this negative through, right? We can think of, maybe this first thing here, n factorial choose 0 as n choose 0 n factorial, and that'll let us rewrite this whole thing as k from 0 to n choose k times n minus k factorial times minus 1 to the k, right? That gives you your sign. But we can do a little bit of algebra to simplify this. The sum goes from 0 to n choose k is simply n factorial over k factorial, n minus k factorial. We have an n minus k factorial, Oof. And we have the minus 1 to the k. So what we can do next is maybe cancel these out, right? We could go so far, if we want to, we could factor out the n factorial as well, and what we get is a alternating sum, k from 0 to n minus 1 to the k, 1 over k factorial. Also expressible, of course, with the n factorial inside your summation, whatever you prefer. All right. Thank you very much. If you have any questions about this, as usual, please let me know somehow. Email me, post in the comments, etc. All right. Thank you very much.